Hello, no, you're there.
Yeah, I'm there. I'm there.
Yeah. So let's wait for the speaker and chair to join. And also remind me to resume the recording. I'll start it when the chair takes over.
Okay, sure. I'll do.
Streaming is already on.
Okay. So you can disable the waiting room
Ah,
in security.
yes. Yeah, done. Hi, Mrinal. Good afternoon.
Hi.
Yeah, so you'll be chairing this session, so I'll just hand it over to you then.
Okay, yeah.
I've made you the co-host, so hopefully, just let me know if there are any technical issues. I'll be
Yeah,
around.
sounds good. We'll do.
Sorry?
Yeah, yeah, sounds good.
Yeah,
We'll
okay,
let you know.
thanks. So
Thank
over
you.
to you then.
Amir, hello.
Hi.
How are things in Israel?
Good, rainy, but good. Yeah, I'm a little bit. I got some allergy today from all days, but I hope it will affect the talk.
Oh,
So just let me know when I should start sharing my PowerPoint.
Amir,
yes.
hi, Amir. I'm Rinal here.
Hi, Wida. Hi.
Hi. Yeah, maybe you should start sharing the screen. We'll maybe start in a couple of minutes.
I think the others, whatever is the banner needs, they should stop sharing, right?
Okay, right. I see.
It's not necessary.
No, it's a co-host. So
Oh, I see. Okay.
he's a co-host, so he can always start in.
Okay. So Amir, currently what is being shared is actually your presenter view in some sense.
So yes, I see that.
So make it full screen, I think.
No, it's not full screen. Probably, I think when you share screen, if you choose the entire screen as opposed to the
Yes,
window.
yes. Yeah, that's
Yeah.
good.
Yeah, now it
It's
works.
better
Yeah.
now, right?
Now it's fine. Yeah.
Yeah, it's okay. Yeah, you can see all my secrets if I show the presenter screen, right? So, en passant, so I spoke with Prahlad a few days back and told me about your efforts to fight COVID with all your research. And,
Sure. Yeah, it's been an interesting year.
to say the least,
Yeah.
yes.
Yeah.
Nitin, so we start on time or a couple of minutes late? What's the protocol?
We can start now.
Okay, all right.
Yeah, in 1 minute we can start.
Okay, okay, we'll do that. By the way, Amir, will you take questions in the middle of the talk, or would you prefer them to come?
Sure. I mean,
That's
we'll take questions in the middle, but I mean, I'm not sure that I will be able to follow the chat. So.
I'll follow the chat, and if there are questions there, I'll...
Okay, thanks. I'm too old to adapt to this new technology.
Yeah. Okay, so maybe let's get started. Hello, everyone. Yeah, thank you for joining this session. So we have an invited talk by Amir Shpilka. Amir is a professor in the CS department at Tel Aviv University. He got his PhD from the Hebrew University in 2001, where he was advised by Avi Vigderson. And following this, Amir spent nearly a decade as a faculty member in the CS department at Technion before moving to Tel Aviv in 2014. Amir's research interests are broadly in complexity theory and particularly in algebraic complexity, algebraic coding theory, algebraic property testing, pseudo-randomness, etc. And today he's going to tell us about some recent advances in algebraic complexity. Amir, over to you. Yeah.
Okay, thanks, Guinal. Thanks for the introduction, and thanks for the invitation to speak at this conference. So I'm going to speak about algebraic complexity, and some of the greatest experts are in India. So I'm sure that many of you know about this subject, but still, I'll speak about that. Okay, so what I want. Okay, so the goal of the talk, I want to introduce algebraic complexity to those who don't know it. I'll speak about the computational model, the important problems, what is the relation to the more traditional complexity theory that we learn, and also why I think everyone should focus on algebraic complexity before starting to separate P from NP. And then I'll speak about some approaches to the P versus to the VP versus VNP problem. One of them is the geometric complexity theory. Then I will speak about some new result or more or less new observations that I made with a student of mine that may be easier to follow than the big program of the GCT. Okay. So algebraic complexity basically studies the resources required for computing algebraic problems using algebraic means. So by algebraic problems, we mean polynomials. So one polynomial is matrix multiplication, right? Every output is a degree 2 polynomial in the input. Similarly, discrete Fourier transform, the determinant polynomial, determinant of a matrix is of course a polynomial. And the determinant is an important polynomial for us, and we'll speak about it later. And another important polynomial is what's going on? The keyboard is stuck. Okay, it's the permanent polynomial. Okay, so just notice that the permanent versus determinant, the only difference is the sign, right? You have the same set of monomials, but with positive coefficients. So these are examples of algebraic problems, and by algebraic means we mean we want to compute those polynomials using the arithmetic operations, and we think of every arithmetic operation as one unit cost. Okay, so let me now introduce the model of computation, and the model is the model of algebraic circuits. So similarly to Boolean circuits, algebraic circuits are directed as cyclic graphs. So the leaves are labeled by inputs or by constants from the fields. So there is always an underlying field F. And for the purpose of the talk, you can think about the field as being the complex numbers or the real numbers or some large field. The internal gates of the circuit are labeled by either plus or times gates. So naturally, every gate in the circuit computes a polynomial in the natural way, right? This gate computes x1 plus x2. This gate computes the product of these two polynomials, etc. Okay, so let's try to see what's the differences between this model and Boolean circuits. So this model seems stronger. Why? Because you can use constant from the field, right? Here I only used one, but for example, if you work over the real numbers, you can plug in pi or e or square root of 2 or 17, etc. So you have more constants to play with. On the other hand, we want to compute polynomials. So we insist on syntactic computation. When we want the circuit, the output of the circuit to be the same polynomial that we want to compute. If you think about Boolean circuits, they always compute a function. So in the Boolean world, if you do x and x, it's the same function as x, right? Or x is the same function. So we have many different representations for the same function, but here in the algebraic world, we insist on one specific representation. So it's not hard to see that if the field is infinite, then every polynomial has a unique representation. You cannot represent a polynomial in two different ways. But when the field is small, this can be you may have more than one polynomial representing the function. So we insist on computing the polynomial exactly. So what are the complexity measures associated with circuits? Well, one of them is the size of the circuit, which is just the number of wires that you have in the circuit. Another measure is the depth of the circuit, which is the length of the longest input-output path. So in this example, the depth is 3, right? We have length 3 path between inputs to outputs. And let me now introduce another notation that will be useful later for this specific circuit. So the top gate is a sum gate. So we represent it by a summation symbol sigma. Then we have a layer of product gates. So we represent it by pi. And then another layer of summation gates. So such circuits are called sigma pi sigma circuits. And whenever I speak about sigma pi sigma circuits or formulas, I will mean that we have sums of products of linear functions. And just notice that every gate at the bottom computes a linear function. Okay, so this is the model of arithmetic circuits. And another model that will be important for this talk is that of an arithmetic formula. So the only difference between circuits and formulas is that in formulas, the computation graph is a tree. So the fan out of every vertex is 1. Okay, so right. So this is a circuit. You may have fan out 2, but in a formula, fan out is 1. Okay, so this is the model of computation. I hope that it's clear. And now let me speak about what are the important problems that we study in algebraic complexity. So of course, the natural problem is to design efficient algorithms. For example, first algorithms for matrix multiplication. Now, if you think about it, all the algorithms that we have for matrix multiplication are basically done by algebraic circuits. We don't call it an algebraic circuit, right? We don't call Strassen's algorithm an algebraic circuit, but it is. It can be represented by an algebraic circuit, right? So we want to come up with new algorithms or with efficient circuits for natural problems. Another question from the complexity point of view is proving lower bounds. It's proving that some explicit family of polynomials cannot be computed by polynomial size algebraic circuits. And the main example is the permanent polynomial that we discussed earlier, that we defined earlier. And the main question that we'll speak about later is showing that the permanent does not have polynomial size algebraic circuits. And this is known as the VP versus VNP problem, where V stands for Valiant. And we'll also see that the question of separating permanent from polynomial size circuits is analogous in some sense to the Boolean problem of separating the class NC of computations that can be done in polylog space from the class sharp, which is a very strong Boolean class. Okay, so this is just an example of the problem of proving lower bound. And another important problem for us is the problem of de-randomization, of studying the power of randomness in algebraic computation. And the main question here is to de-randomize what's known as the polynomial identity testing question that we'll discuss later. Okay, so these are the main problems, right? Coming up with new algorithms, proving lower bounds, and understanding the power of randomness. Very similar to what happens in the traditional computational complexity world. Okay, so now let me speak about this VP versus VNP problem and the connection to the Boolean world. Okay, so we'll speak about Valiant's hypothesis. So remember, Cook-Levin theorem basically says that all explicit puzzles, and by that I mean problems in NP, reduce to SAT, right? So they are just SAT in this case. So Valiant basically showed that all explicit polynomials, and I don't want to define this notion formally, just think about it as all polynomials where if I ask you what is the coefficient of a certain monomial, you can tell me efficiently what this coefficient is. So for example, in the permanent, right, if I give you a monomial, you can tell me whether the coefficient is 0 or 1 quite easily. Right, so all explicit polynomials are just permanent in this case, so they reduce to permanent. And all efficiently computable polynomials, those that have polynomial size circuits, are just determinant in this case. So they reduce to determinant. And here I'm just making life a bit simpler because determinant is not complete for this model exactly, but for some other model, but let's not worry about that. Okay, so what is the notion of reduction, right? If you want to say that some polynomial is complete, so you need to define reductions. So in a reduction in the algebraic world, we say that f reduces to g if basically f is a projection of g. And by that we mean that you can take the variables of g, replace them by linear functions in the variables of f, and then once you do it, g composed with those linear functions compute f exactly. Okay, so this is very similar to what happens in the Boolean world when you do reductions, right? One language reduces to another if for every input to the one language you can come up with an input to the other language, the decision problem, the answer to the decision problem is the same. Okay, so this is the notion of reduction. You just replace variables with linear functions. Okay, and then using this notion of reduction, roughly, and this is a bit cheating, Valiant showed that the determinant is complete for algebraic P. Algebraic P is all the polynomials that have been computed by polynomial size circuits. And again, if I want to be completely accurate, I have to speak about families of polynomials with number of variables going to infinity, etc. But let's not worry about that. And the determinant is complete for algebraic NP. And so the determinant captures easy computations and permanent captures hard polynomials in some sense. And as I said, there's a small caveat that determinant is actually complete for some slightly weaker model. But again, let's not worry about that. Okay, and Valiant's hypothesis is that VP, right, the class of efficient computations, is different from VNP. Or in other words, that the permanent does not have polynomial size algebraic circuits. Okay, so that's the VP versus VNP problem, which is the main problem in algebraic complexity. Okay, so let me now discuss the connection between Valiant's hypothesis and Levin, the Cook's hypothesis. Okay. Something is wrong with the keyboard. Okay, so recall that Valiant showed that permanent is permanent with 0, 1 entries is complete for the class sharp P. That is, computing the value of a 0, 1 permanent is complete. And then building on Toda's theorem and another beautiful theorem that we'll discuss shortly, that every algebraic circuit can be made to have depth polylog, we get the following beautiful connection that if we can prove that VP is equal to VNP, when we have to distinguish between the different fields that we work over, but over C, for example, and we assume the generalized linear hypothesis, then we get the following collapse in the Boolean world, right? That P/poly equals N P/poly. Or if you work over finite fields, you don't need any hypothesis, and it shows that P/poly equals N P/poly. And in either cases, the polynomial hierarchy collapses. So if your life goal is to separate P from NP, or to show that NP does not have polynomial size circuits, then you should start by proving that permanent does not have polynomial size algebraic circuits, right? Because this would be a corollary of NP not containing P/poly. Okay, so this is why I think that everyone should study algebraic complexity if you want to understand the P versus NP problem, because the main problem of algebraic complexity is a corollary, of course, if you believe that VP is different from VNP, of the NP not containing P/poly. Okay. So you may say, okay, but this can be as difficult as the NP versus P/poly problem, but actually there are some reasons for optimism, in my view. So the first of them is the theorem that I already mentioned, that VP equals VNC squared. And more formally, it says that if a polynomial can be computed by a circuit of polynomial size and polynomial degree, so the polynomial that you compute is a polynomial degree, then it can also be computed by polynomial size circuits of depth only log squared. Okay? So basically, it says that efficient algebraic computations are shallow. In the Boolean world, we don't have this, right? We believe that NC squared is different than NC cubed, different than NC 4, etc. And they're all different from P. Okay, so this is a weakness of the algebraic model that maybe we can exploit to separate VP from VNP. Another beautiful recent theorem is that VP, again, class of efficient computations, is contained in sub-exponential depth 4 formulas or depth 3 formulas. Okay, so remember, these are the formulas that have a plus gate at the top, then a layer of product gates, then sum gates, and product gates. So a sub-exponential depth 4 formula, at the bottom two layers computes polynomials with a sub-exponential number of monomials, then takes such products and sums. Or even if you work over the complex numbers or characteristic 0, VP is containing sub-exponential depth 3 formulas. Okay, so think about it. If you want to prove that VP is different from VP, you just need to prove that permanent requires exponential size depth 3 formulas. Also, you just need to prove a very strong lower bound, but for a very restricted model. Okay, and nothing like that is known in the Boolean world, and we don't even believe that such things hold in the Boolean world. Okay, so again, this gives reason to believe that maybe in the algebraic world you can separate VP from VP. And furthermore, there's a long line of work that shows sub-exponential lower bounds for that 4 circuits. Unfortunately, those sub-exponential lower bounds are not strong enough to separate VP from VNP. But we can hope to do something better. For example, you can ask, maybe you can improve the sub-exponential here so that these lower bounds will separate VP from VNP. But unfortunately, this is also not possible by some other reasons. Okay, so what's the take-home message? So take-home message, I think, is that exponential lower bounds for very low depth algebraic circuits is enough to separate VP from VNP. We are not there yet, but again, this is a very strong restriction on the model. Right? This is something that gives reason for optimism that we can prove lower bounds. Okay, so this is what I wanted to say about the model and about the lower bounds. And now let me move to the next question of de-randomizing polynomial identity test, which for short I call PAT. Okay, so what is the PAT problem? We are given a circuit phi from some class of algebraic circuits C, right? So you can think of C as being just polysize algebraic circuits or algebraic formulas or depth 3 circuits, etc. So we are given that circuit, and we want to deterministically decide whether the circuit computes identically 0 polynomial. Another way to think about this problem is that we are given 2 circuits from the class, and we want to check whether they compute the same polynomial. Okay, very natural problem. So why do I insist on deterministic computation? Because if you think about it for a second, this is very easy if you are allowed to use randomness, right? Because if a polynomial is non-zero, then it does not vanish on a random input, right? The set of zeros of a polynomial is a set of dimension 0. So a random input will be with high probability a non-zero of the circuit. So with randomness, you can solve this problem quite easily. Okay, so we want to deterministically decide if the circuit is 0. Now we have the question, how is the circuit given to us? So there are 2 versions for the problem. One of them is the white box version, in which we can see the circuit. By that I mean that the circuit is given to us. We get the graph of computations, we see all the constants and all the variables on the leaves, etc. So we have the circuit in front of us, and we just have to decide whether it outputs 0 or not. Another more difficult model is the black box model, in which the circuit sits in some black box, and our only access to the circuit is the only thing we can do is give some input to the circuit and get the value of the circuit on that input. Okay? So this is a very restricted model. You can just query the circuit at some point and get the answer. But still, if you think about what I said here about how you solve PAT with randomness, it's done in the black box model, right? You just sample A randomly, and you look at the output. Okay, so how can we decide PAT in the black box model? Right, so think about it. You give an input to the circuit. So of course, if you get a non-zero output, you say the circuit is non-zero, right? So basically, your algorithm looks like that. You feed an input to the circuit, you get 0. You feed another input, you get 0, until the first time you get a non-zero. Then you declare that the circuit is non-zero. So So in other words, an algorithm for PAT in the black box model is equivalent to a heating set for the class. What's a heating set? Heating set is just a set of inputs such that every non-zero circuit in the class must evaluate to non-zero on some input from the set. Okay, in other words, it's a set of inputs that hits the non-zeros of every polynomial from the class. Okay, now you can ask yourself, do we have a polynomial size heating set? Is this even a reasonable task? And the answer is yes. And there's a nice theorem by Einstein that says that if you pick the set H randomly, with all coordinates being integers between 1 and s times n squared, where s is the size of the circuit in the black box and n is the number of variables, and you just need your set to be of polynomial size, then with high probability, this set hits every size s set. So efficient hitting sets exist, and the main question is finding one explicitly. Okay, any questions about the problem, the model, the white box versus the black box settings? Okay, so why do we care about the PAT problem? So for me, the most, the best reason is that I think it's a very natural and fundamental problem, right? Understanding the power of randomness. If you look at algebraic algorithms that use randomness, basically, more or less, each one of them is using randomness to solve PAT, right? So that's what I mean. PAT is more general algebraic problem. But if you are not convinced by that, there are other reasons. One of them is that there is a strong connection to circuit lower bounds between the randomizing PAT and proving lower bounds. And I will speak about it in the next slide. But there are also other algorithmic importance. The primality testing algorithm of Agarwal-Kayal-Saxena is done by solving some explicit PAT problem. And in recent years, we have deterministic algorithms for solving perfect matching in graphs in parallel. So the polynomial time algorithms that we have for perfect matching are sequentials. They use n sequential steps. And there's a very simple randomized algorithm that uses log squared term. And recently, by derandomizing some PAT problem, we have algorithms for perfect matching in depth polylog. They're still not polynomial time, they're only quasi-poly time, but still they are the best parallel algorithms that we have for this problem, deterministic parallel algorithms. And it also gives us some intuition for the randomization problems in the Boolean. Okay, so we have many reasons to study this problem, but again, I liked it because it's natural and fundamental. Okay, oops, sorry. So let me now speak about the connection between derandomizing PAT and proving lower bounds. Okay, so here we have the goal of proving lower bounds. Here we have the black box model and the white box setting. Okay, so let's try to understand the connection between those different questions. So clearly, if you can do PAT in the black box model, then you can do PAT in the white box model, right? If you can decide PAT without looking at the circuit, then you can certainly decide it when you have the ability to look at the circuit. Okay. Now, Einstein also showed that if you have black box PAT, then you get lower bounds. Why is that? Because recall that the black box PAT is giving a heating set, such that every non-zero circuit in your class vanishes on that heat. It does not vanish on that heating set. So if you can come up with a polynomial, a non-zero polynomial that vanishes on the heating set, then it cannot be computed in your class. Okay, so that's again very simple. And what about the other errors? So Kamenetz and Palazzo showed a beautiful result that says that if we have sub-exponential time PAT algorithms, even in the white box model, then they imply lower bounds. And if we have lower bounds, then they imply black box PAT algorithms. And this is done similar to the Nissan-Wigzron generator. I will not discuss it further. But you see that we have a full cycle. So all these problems are more or less equivalent. Of course, you get you don't get you lose a bit in the parameters when you complete a full cycle, but still they are very tightly related. Let me mention another very beautiful recent result that says that, I don't want to get into the exact details, but if you can save even 1 point on the trivial PAT eating set construction, and the trivial construction is just giving the trivial interpolating set, then you can leverage this to a full-fledged PAT for general circuits and get lower bounds, etc. Okay, so that's another reason for optimism, right? You just need to do something that's slightly non-trivial, and then basically you solve the problem. Okay, good. So let's summarize this part. So we gave the basic definitions. We discussed the Valiant's hypothesis, the VP versus VNP. I explained why I think it should be tackled before P versus NP. We discussed the PAT and the connection between those two questions. What I want to do next is speak about the two approaches for the VP versus VNP problem. One of them is the GCT problem of Mulmulé and Sohoni, and then I will speak about a work I've done with my student. Okay. So GCT. So we call that we want to, since the determinant is complete for VP and permanent is complete for VNP, we want to show that we cannot reduce permanent to the determinant. In other words, we want to show that permanent is not a linear projection of the determinant. That is, if you get a matrix X for the permanent, you cannot just take a matrix, maybe slightly larger matrix, for, such that each entry of that matrix is a linear function in those variables, such that the determinant of that matrix gives you the permanent of X. Okay, so again, think about AX as a large matrix in which each entry is a linear function in those variables. We want to show that if you can do this, then the matrix here that you have inside the determinant is huge. It's not polynomial size. Okay. Now, if you think about what's happening here, basically, this is the composition of the determinant of some huge matrix with some linear map, right? It tells you at each coordinate which linear function to write. So you can think about this composition as the action of this matrix A on the determinant polynomial, where the action is the following. Given a matrix, the way that it acts on a polynomial, just let the polynomial act on A times X. Okay? So this matrix A tells you how to replace the inputs with linear functions. Okay. So now we want to show that permanent is not in the orbit of the determinant. What I mean by that? I mean that if you look at the determinant of M by M, and think about M as being, you want to show that permanent of an N by N matrix cannot reduce the determinant of a poly N by poly N matrix. So think about M as being some polynomial in N. And then you take all the set of matrices taxed on the determinant, so it gives you many different polynomials. So we call this the orbit of determinant under the action of this family of matrices. And you want to show that permanent is not one of the polynomial in your family. Okay? So again, there's a small caveat here that permanent is a degree n polynomial and determinant is degree m polynomial. So m is larger than n. So just to make the degrees the same, we just look at some padding variable c and look at this polynomial. We want to show that that polynomial is not in the orbit of the determinant. Now, here we have to consider all matrices, and somehow considering, and the set of all matrices is not a multiplicative group, right? Because some matrices are not invertible. So if you think about it for a second, you can see that every matrix is the limit of invertible matrices, right? You can, there's a sequence of invertible matrices that converge to, so for every matrix H, A, there's a sequence of invertible matrices that converges to A. So in other words, you can think about that what you want to study is the orbit of determinant under invertible matrices. And since determinant is, we look at matrices, M by M matrices, right? So we have M squared inputs for the determinant. So we have to look at the group that acts on M squared inputs. So this is the general linear group on M squared variables. And now we don't just look at the orbit, but since we have to take also limits, we look at the closure of the orbit. What do I mean by closure? So every polynomial you can represent by its coefficient vector. So when I speak about closure, you just take a limit point of coefficient vectors in your orbit. Okay, so you want to show there is no sequence of invertible matrices such that when you apply them on the determinant and take the limit, you get a point. Okay? So this is equivalent to showing that permanent is not a projection of determinant. This is just an equivalence. Okay. And now here's the nice fact that that's the basic of GCT. And the fact says the following. If we want to prove that permanent is not in the closure of the orbit of determinant, and if this is indeed the case, then there's a witness for that. This witness is called the separating polynomial. And basically, this is a polynomial, capital F, that takes as input coefficient vectors of polynomials. Right, so think of F as a polynomial in a huge number of variables that takes as input coefficient vectors of degree m polynomials in m square variables. Right, for example, one coefficient vector is coefficient vector of the determinant polynomial. So this polynomial takes as input coefficient vectors, and we want, if permanent is not in the closure of the orbit of the determinant, there is such a polynomial f that vanishes on every polynomial in the orbit of the determinant, but it does not vanish on the coefficient vector of permanent, or more accurately on the padded permanent. Right, so if you have such a polynomial f, then clearly permanent is not in the orbit or in the closure of the orbit, right? Because the polynomial vanishes on everything in the orbit, but it does not vanish on the permanent. Okay? And since things are continuous, it's enough to just study the orbit, not the closure, because if a polynomial vanishes on things in the orbit, then it also vanishes on things in the closure of the orbit, right? If a polynomial vanishes on the set, it also vanishes on the closure of the set, right? So this is basically what we want to show. We want to show that there exists a polynomial f that vanishes on every coefficient vector in the orbit of the determinant, but does not vanishes on the coefficient vector of the permanent. And the GCT approach by Formula and so on is to look for such a polynomial f using representation theory of the invertible matrices. Okay, so let me just give a picture of that, and then maybe I'll say a word about why representation theory. Okay, so again, so what's the picture? So think of this is the space of all degree n polynomials in m square variables. And one of the coefficient vectors is that of the determinant, and the other one is that of the padded permanent. And now you start looking at the orbit of the determinant. So each matrix A, when you compose it with the determinant, gives you another polynomial, and another polynomial, and another polynomial, and that gives you the orbit. Right? All the polynomials that you get by applying invertible matrices to the determinant. And now you're looking for a polynomial f whose zero set contains that orbit, but it does not contain the point. And such a polynomial f is a separated polynomial that you're looking for. Okay, so that's basically how we should separate. So if permanent is not in the orbit of the determinant, then you know that such a polynomial capital F exists, and you only have to find it. And the GCT approach is to find it using representation theory. So I have one slide about that, and bear with me. If you don't want to hear about representation theory, you can just tune off one slide, and that's it. Okay, so why representation theory? So as we said, the separated polynomial f, you can think about it that it comes from a vector space of all the polynomials that act on coefficient vectors, right? Those polynomials in a huge number of coordinates. And now we can use, so recall we said that GLN square acts on the determinant, right? You can compose it with the determinant, but you can also think about it as acting on the space V, right? Because if you have a polynomial in that space, how does A act on F? So it should give you another polynomial in that space. And how this polynomial acts when it's given a coefficient vector, it just equals to the value of f on input this polynomial. And we already know how matrices act on smaller polynomials. Okay, so this, it looks like it can look mysterious or just some abstract nonsense, but that's something very natural to look. Right? If a matrix acts on a space and you have polynomial acting on that space, so you can think of the acting of the matrices acting on this large polynomial. Okay. So such an action is called a representation of the group GLM squared. Okay. And if we consider all those polynomials that vanish on the orbit of determinant, or all those polynomials that vanish on the orbit of determinant, then they define something that we call a subrepresentation. So recall that we want to find a polynomial f that vanishes on the orbit of determinant and does not vanish on the permanent. But we don't even have to find it, we just have to prove the existence of such a polynomial. And this is exactly what the GCT aims to do. The GCT wants to say that, okay, let's look at those subrepresentations and prove that they are different in some sense. And we don't want to get into which sense they are different. And if they are different, then this guarantees the existence of a good separating f. So we don't have even to construct f explicitly, but by studying representations and showing that they are different in some sense, this is enough to separate VP from VP. Okay, so everything boils down to some questions about those subrepresentations of the general linear group. But unfortunately, it seems that the relevant representation theory questions of studying those subrepresentations are very difficult. Okay, but that's basically the GCT approach in a nutshell. Okay, so what I want to do next is present a different approach that is based on a joint work with my student Dori Medini, that I think gives a much simpler setting and also some reasons to be optimistic about why this may work. Okay. So remember that GCT considers closures of orbits, right? The closure of the orbit of determinant. And why do we consider determinant? Because determinant is complete for VP, or more or less. But we don't actually need to consider, but we can also try to come up with a polynomial that is not complete for VP, but whose closure gives you everything. Right? And instead of looking at determinant, look at that other polynomial. Okay, let me give you an example because we are not the first to think about it. So let me just give another definition. What we call a V2 algebraic branching program, or ABP for short, is a computation that looks as the following. You have a sequence of 2 by 2 matrices. Each entry so each matrix has 4 entries, and each entry is some linear function. And the polynomial that you compute, you just take the product of all those matrices, and your output is just the one entry of the product. Okay, so this is the model of computation. You have 2 by 2 matrices, you have D of them. Okay, D is just a parameter, D is the complexity of the computation. And you plug in linear functions as entries, and you compute the product, and you take one of the entries of the output. Okay, so this is a computational model. You can ask, what's the strength of this model? So here's something, a very nice result of Algebraic one, which says, even this simple polynomial in 16 variables cannot be computed with this model. Okay, so this is an extremely weak model. It cannot even compute this simple degree 2 polynomial. Okay, so why do we care about that model? Because there's a very nice result from recent years that shows that if you take the closure of all such ABPs of polynomial size, so polynomial size means that this D is polynomial in N, then this closure contains all polynomials that have poly-size formulas. Okay, so poly-size formulas we denote by VP subscript E. E is for polynomial, for expressions, but basically don't need to remember that. So again, so we have a very simple model, a very restricted model. It cannot even compute this polynomial that certainly has a very small formula. Yet its closure contains all polynomials that have polynomial size formulas. Okay, so instead of studying the determinant, maybe show that the determinant is not in the orbit of that model. Okay. Okay, and what is the orbit now? You can just take the canonical V2 ABP. What do I mean by canonical? You can think about every matrix here as having 4 formal variables, x11, x12, x21, x22, and each of these matrices has 4 different variables. And then again, you just replace those variables with linear functions. So this is again the action of the group on that polynomial. So instead of studying the action of the group on determinant, you can study the action on this simple polynomial. So this is very nice. And again, this is not my work. So what the only thing that I don't like about this model is that we still don't understand it quite well enough. For example, we don't even have PAT algorithms for this model. And by this model, I mean when you have linear functions. Okay, so this is a nice open problem. I don't think it should be that difficult, but currently we don't have PAT algorithms. Okay. So now let me talk about my work with Dori. Okay, so again, remember that what we want to do is to look at orbits of simple polynomials, such that those orbits capture something interesting. Right? So here's a simple observation. Let us consider Rydwan's formulas. So what is a Rydwan's formula? So you remember, formula is an algebraic circuit whose computation graph is a tree. Now a Rydwan's formula is a very weak formula. It's a formula in which every variable can label at most one leaf. So every variable appears only one at the leaf level. So clearly the size of such formulas is almost linear, n, right? Because the number of leaves is just the number of variables. So this is an extremely weak model, okay? However, if you look what happens when you replace the inputs x1 up to xn with linear functions, with linearly independent linear functions, so you don't get Rydwan's formulas, but you get Rydwan's formulas composite in vertical matrices. And now if you take the closure of all the polynomials that you get in this way, then immediately it's a very simple observation. You get all the polynomials that have size m formulas, right? So if you take Rydwan's formulas in m variables, and you look at the orbit under GLM, then you get all size m formulas. This is quite easy. Okay, so what's good about this model? Well, we just showed that we can find the heating set for that model. So this is now very interesting. So we need to study closures of orbits. This will give us all the formulas, basically. But so what we have is a heating set, not for the closure of the orbit, but for the orbit itself. Okay, so if you think about it, we have a dense set. This is all those polynomials of the Rydwan's formula composite in vertical matrices. They are dense in the set of all polysize formulas. And we have a very simple heating set for this model. And furthermore, there is also a reconstruction algorithm for polynomials computed in this model. And the reconstruction algorithm means that if you give me a black box access to such a polynomial, a Rydwan's formula composed with a matrix, then there is a randomized algorithm that makes queries to the formula and reconstruct and completely builds the formula. Tells you what are the linear functions at the bottom layer, and what the formula is. And furthermore, our result shows also so this is a randomized algorithm. Our result shows also an information theoretic deterministic reconstruction. And by that I mean that there is an algorithm that makes a quasi-polynomial number of queries to the formulas, a deterministic set of queries, right? Queries that it knows in advance. Basically, it queries the formula on that heating set. And from the set of values can reconstruct the formula. Now, the computation is not efficient, but it's deterministic. So that's why I call it information theoretic reconstruction. Okay. So this is for VPE, the class of polynomial size formulas. And what we want to do is just extend this heating set from this orbit to the closure of the orbit. So you can say this can be difficult because it will give us a heating set for the class of all formulas, and because of VP equals VNC squared, it also tells us something very strong about circuits. So maybe you should try to study this approach in a simpler mode.
Amir,
Yes.
a quick question. So here the reconstruction algorithm is in the worst case, or is there some average case assumption here?
No, so here it's in the worst case because we only consider Rydwan's formulas composed with invertible matrices. So indeed, the original paper spoke about average case. However, if you assume that, because it speaks about formulas in which you have linear functions at the bottom, and there was no assumption that those linear functions are linearly independent. However, if you also assume that they are linearly independent, then you can show that the algorithm works with very high probability on the internal coins, but not. It just works.
Okay, thank you.
So that's just a very simple observation once you look at the algorithm. I mean, it's simple in the sense that if you go over the steps of the algorithm and you see where you needed to assume these average case assumptions, then this is satisfied by those invertible. Okay. By the way, how much time do I have? 7 minutes or 2 minutes?
Actually, about 15 minutes. We have till 3
15
o'clock.
minutes.
Yeah.
Okay. So yeah, okay, great, fantastic. Okay, so now let's look at a different model. Let's look at this very simple polynomial. So maybe it's hard to understand it's simple, but think about a polynomial that has m square variables, and it is just the sum of m monomials, each of degree m. Okay, so you take x1 1 times x1 2 times x1 3 up to x1 m, and then x2 1 times x2 2 up to x2 m, and then you add all those monomials. So you just have m monomials of degree m in different variables. And again, you compose them with invertible linear functions. Okay? And you take the closure of it. So again, it's not hard to see that this closure contains all the polynomials that can be computed by size m, that 3 formulas. So we call what are sigma by sigma? Sums of products of linear functions. Here we have just sums of products. So the composition with GLM square gives you linear functions. But it gives you independent linear functions, but the closure contains everything. And again, what's nice about this model? We have a polynomial size heating set for this model. So here we have quasi-polynomial, here we have polynomial size heating set. We also have a randomized, again, zero error reconstruction algorithm. Here it's also zero error. And also an information theoretic deterministic reconstruction. Again, the same thing, but for a much simpler model. And why do we care about sigma pi sigma? Because we don't have PAT algorithms for sigma pi sigma circuits, and our best lower bound is only cubic. So as a playing ground, you can start testing your ideas using sigma pi sigma formulas, because the big questions are also open there. Okay. So the wishful thinking is that maybe we can take our rating set to get PAT or lower bounds for these models. Because remember, if we have remember the hardness versus randomness connection, if you have a rating set for the model, then you get lower bounds. So here we have a rating set for a dense set, not for the model itself, for a dense set. And maybe we can extend it to a rating set for the entire closure. Okay? So let's think about what's needed to get rating sets for the closure. Okay? So here we come to the notion of a robust rating set. And this is the question of how do we move from rating set for class C? So think about the class C as the real formulas composed with invertible matrices, or that tensor T composed with invertible matrices. And we want to take the PAT that we constructed and get the PAT for the closure, because the closure is what we are aiming for, right? It's sigma pi sigma, or the class of polynomial size formulas. So here's a definition. So we say that the rating set H, a set of inputs for a class C, is a robust rating set if basically a polynomial that is not zero does not get on some input in the set gets a value that is not too small. What do I mean by not too small? So for example, if take the norm of the polynomial, look at the list of coefficients of the polynomial and take their norm. Okay, so you want that at least on some input on your eating set, the absolute value of the polynomial, value of the polynomial at that point will be not too small. It will be at least some epsilon for some absolute constant epsilon. Okay, so again, if you only consider polynomials with norm 1, then each one of these polynomials get a value at least epsilon on some point in your eating set. Okay. So remember, eating sets just tells us that a polynomial gets a non-zero value. And here we also want the assumption that the value is at least some epsilon. And that epsilon is fixed. Okay? So is the definition clear? What's the difference between usual eating sets and robust? So the only difference is that you don't just assume that it's a non-zero value, but you also assume that the value is at least something. And what's so good about robust eating sets? Well, okay, first of all, again, you can ask yourself, do robust eating sets even exist? Well, and again, if you look at the arguments of Einstein Schnorr, again, they did not prove it, but you just go over the proof. So the argument gives you that, yes, the same thing happens. There is a robust eating set with coordinates that are integers with small bit complexity, which is robust for sizeless sets. So again, robust eating sets exist, you just have to look for them. Now, what's so good about robust eating sets is the following. If you have a robust eating set for a class C, then just because of this property that every non-zero polynomial gets value, which is at least epsilon, this is also a robust eating set for the closure of C. Why? Because if a sequence of polynomials converges to a non-zero polynomial f, then you can normalize everything and assume that the norm of f is 1. Then for a large index n, those norm of f and will also be at least, I don't know, half or 0.9 or 0.99. And therefore, there will be some input that gives value at least epsilon. And since h is finite, there will be a subsequence that converges to f, such that for every polynomial in that subsequence on some fixed input a from h gets value at least epsilon. And therefore, this also is the limit. And this is what you get. Okay? So what we want to do now, so we have an eating set for class C. And if we could take the eating set, massage it a little bit, and make it a robust eating set, then this will give us an eating set for the closure of the class. And if you can do this efficiently, then this will give us eating set for sigma pi sigma, or even for polynomial formulas, because we already have eating sets for dense subclass. Okay? So is this clear? So we have an eating set for a dense set. If we could only make that eating set a robust eating set, then we will be done. We'll get eating sets, we'll get lower bounds, we'll get everything that we want. So it seems like a very small step is needed, making the eating set into a robust eating set. Yeah, I was so naive when we came up with this definition of a robust eating set. I just said, okay, you can just give a student the task of just taking every known eating set and making it robust. But now you see that this is actually quite difficult because it will solve all our problems, right? Okay, so unfortunately, okay, you can ask, okay, does the eating set that Dori and I construct, are they robust? And unfortunately, you can show that they are not robust. Why? Because we can show that the arguments that we use to construct our eating sets can give an eating set for which there exists a polysize formula, even a polysize sigma pi sigma formula that vanishes on both eating sets, and a non-zero polysize formula. And since it vanishes on both eating sets, they cannot be robust. Because if they were robust, then no such formula could vanish on them. Okay? So we have eating sets for a dense subclass. That eating set is not robust. We can, or at least a cousin of that eating set that has the same properties, which is also eating set, is not robust. So we did not solve all the problems of, or at least we don't know to say that we solved the problems of PAT for VP or sigma pi sigma. But again, we have some. Okay. Now let me say another word about why I mentioned the reconstruction algorithms. So I want to speak about a special kind of reconstruction algorithms which are continuous. So let's look at some specific example. Remember this T, which is that polynomial, right? Just a sum of m monomials in different variables. And I mentioned that there's an information theoretic reconstruction. So just think about this composition as a map that takes a matrix and gives us a polynomial, right? What's that map? Given a matrix A, just look at the composition of T with A, right? Which is, since we have m square variables and I label them by 2 indices, this is what happens when we compose the matrix, right? Think about A as having m square rows, m square columns, and I index rows by pair of indexes, and I index columns by pair of indices. So this is how I compose T with A. That's the polynomial that I get. So you take a matrix A and it outputs the coefficients of this polynomial, right? Just think about it as some abstract way, some abstract map. Okay, takes an invertible matrix, it outputs a coefficient vector. What do we know about this matrix? Remember, I said that we have a deterministic reconstruction. So in other words, we have a set H such that this mapping is essentially one-to-one. What do I mean by essentially? That's not completely accurate, but this is what I mean. I mean that if you look at the list of values of that polynomial evaluated on the points in the eating set, they completely determine the coefficient vector. So since evaluating at a point is a continuous map, the inverse function theorem tells you roughly, I don't want to get into the specific conditions, everything, that going back from that set of values to the coefficients is locally continuous. That is, for every point here, there's a small neighborhood in which that map is continuous. Okay, so you can say, so what? What does it tell you? However, if you could make that inverse map continuous at 0, just one point, and notice that 0 is not in our set because this polynomial is not 0, so it gives some value here is not 0. So the 0 point is not in our set. Just the light turned off in my office. Okay, never mind. I sit too still. I should move a little bit, be more engaging. So if we could make our algorithm deterministic continuous at 0, then this will give us a robust eating set. Why? Well, okay, I will not prove it, but you can think about it a little bit and understand why. Yeah. So, okay, we have a reconstruction algorithm. It's locally deterministic. Maybe you can massage it to get a reconstruction algorithm that will also be locally continuous at 0. And a deterministic reconstruction algorithm basically is an algorithm that makes queries and then reconstructs. So the set of queries is our robust eating set. So that's another approach to constructing robust eating sets. Okay, if you can see this, I can stay after the talk and tell you the one-line proof of why this is enough. Okay, so let me just show you the map of what we have. So think about, again, this ellipse as the space of all coefficient vectors of degree n polynomials and n square variables. Yeah, so I should have written m and m squared, never mind. Okay, so the dimension is exponential. Okay. Inside it, let's focus on sigma pi sigma. You have all the coefficient vectors of polynomials that can be computed by size n sigma pi sigma series. Okay, it's a subset. Here we have the set of n square by n square matrices. Remember, we have n square variables and we want to apply invertible matrices. Okay, and we only want to look at the non-singular matrices, right? So we cut off the singular matrices and we move. And we have a map. Okay. And we have a map. What's the map? The map takes a matrix A from here and maps it to the coefficient vector of T composed with A. Okay, that's the map phi that I described earlier. We also have, and what we said is that the image of this map is dense, right? So this scribble is supposed to be dense. Okay. So this thing is dense inside sigma pi sigma. Okay. We also have a eating set. And moreover, eating set that has a very nice property, the following. So let's look at the eating set, and let's look at the space where I have the dimension is the same as the size of the eating set. And now, what our theorem tells you that H is such that this map that takes a polynomial from here and maps it to the value on the eating set is 1-to-1. Okay, so basically you have this dense set, and if you look at what you get when you evaluate every polynomial in the dense set on H, you get some set here, right? And this matrix, this invertible matrix here was mapped to a polynomial here, and that's the evaluation vector of that polynomial. Okay. Now, we want this set to be robust. So in other words, we want to say that if we look at polynomials that have norm 1, we want that the set of values, at least one value will be at least epsilon. So you want this set of evaluations to be far from 0. But unfortunately, our set is not robust. So 0 is a limit point of those evaluations. Okay? So if we could find such a set H, such that this map is such that if you only restrict yourself to polynomials of norm 1, you want 0 to not be a limit point on that value, on those evaluations. Okay? And the inverse map, what I said is locally continuous. And what do I mean by locally continuous? Well, okay, I don't want to get into too many details, but basically you can look at the manifold, which is the closure of that map. And on that manifold, this inverse map is locally continuous, except at 0. Well, 0 is not a point in our manifold. It's in the closure, but not in the dense set in the manifold. Okay, so let me summarize. So this is the new approach. We have a dense set of polynomials inside VP, the polysize formulas, and inside sigma by sigma. Each of the dense sets is the orbit of a single simple polynomial. And we also have a eating set H, which is more than an eating set. It also determines the polynomial, right? The list of evaluations on H of every polynomial in the orbit is unique. But unfortunately, H is not robust. And the reconstruction algorithm is not continuous at 0. But still, there's reason to be optimistic, right? Because we have a eating set, a non-trivial eating set for a dense set. And we only need to massage it to make it robust. And once we do this, this will give us a robust eating set and therefore a eating set and lower bound for the superclass. And that's all we need to do to solve the big problems of algebraic complexity. Yeah, so that's it. That's what I wanted to say. And thank you. And I think that now you have all you need to separate VP from VNP. So I expect to hear from you shortly.
Thanks, Amir. Yeah, we have time for questions. So just unmute yourself and feel free to ask.
Yeah, may I ask a question?
Yeah, sure, go on.
Oh, hi, Amir. This is Albert speaking.
Hi, Albert.
Okay, so the question is a bit high level, so it's from the first part of the talk. So I wanted to know about, I mean, the goal is, of course, to show that the permanent doesn't have this circuit. But, and you focused on VNP because that's the class of the permanent. But the question is, since this is the analog of sharp P, the question is whether there are analogs of higher classes. And in case there are analogs like exponential time, for example, and if there is such an analog, how do you prove lower bounds for those? Is it easier or what are the techniques?
Okay, so you need to, so basically VNP captures sharp in some sense, right? So you need to look at the higher levels, like where you don't even have, you don't know the connection between sharp P and the exponential time, etc. So yeah, so I mean, okay, right. So you can take any language, right, which is in EE, triple E, whatever, right, and look at the multilinear polynomial. So for every, right, so a language, you can just look at the restriction to inputs of length n, right? And for inputs of length n, there's a multilinear polynomial representing that language, right? That tells you 0 or 1 if the input is in the language or not. So you can just look at this family of polynomials and ask your question about it. So again, I mean, you can probably use diagonalization arguments to separate such classes, but you don't have any other techniques, right, to separating them. But that's, I mean, you basically want to take a Boolean language, translate it to a sequence of multilinear polynomials, and then study the complexity of those polynomials. Right?
Okay, thanks.
Any more questions?
So Amir, so there's this general connection that you have from lower bounds to constructing heating sets. Like if we have a strong enough lower bound, we get a suitable heating set or something. I mean, is it conceivable that there is a suitably strong enough lower bound that may give you a robust heating set, or even
yes, so if you have a
candidate for something?
Right, if you have a lower bound for the closure of the model, then it gives you a robust heating set, basically.
I see.
Okay, because this is also because, right, if you think about the commenting Paleot's approach, right, if something is not a heating set, then you factor and you find something. And Burgisser showed, right, that if
the factors
right, I mean, starting at factors of closure, then it's a limit of something.
Amir, so you have this general connection for depth 3 circuits. Does it become any better if you focus on some restricted classes like bounded top fan in depth 3, or results for which results are already known, PIT results in the classical model?
Yeah, so I did not, I mean, this is the kind of things I did not look at this. I thought I'd give it to a student, as I said earlier.
Okay.
This should be doable. I mean, I don't think that's very difficult. Of course, I mean, there's a small caveat, right? I mean, Muginal showed that, right, if you look at depth 3 circuits with top fanning 2, then every polynomial can be computed, can be approximated by such a model.
Mm-hmm.
Right, so when you take a heating set and you make it robust, it should take into consideration the degree of the circuit as well. But that's fine. I think that should be possible. But for example, another question that I didn't mention here, or another model, is what you call depth 3 powering circuits, right? That you have the sum, but now instead of product of linear functions, you just take one linear function and look at its power. So again, you can look at the simple polynomial x1 to the n plus x2 to the n plus xn to the n. Look what happens when you compose it with invertible matrices. So this gives you a subclass of what you call depth 3 powering circuits. And again, it's trivial to get a poly-size heating set for that class. And we also have a heating set for the closure of this map, right? We have a heating set for depth 3 powering circuits. That heating set is of size n to the log n. So as a first attempt, maybe you can try to take the poly-size heating set for the dense subset and make it robust, so that it will give you maybe a better heating set for the closure. Okay, this is also something that I could have mentioned, but I thought that there will be too many classes. So again, this is something very simple. You can take it, I mean, everyone can take this as an exercise, look at the polynomial summation of xi to the n, compose it in an invertible matrix, find the heating set for this model. There's a very simple heating set for that. And now try to make that heating set into robust, hoping that you'll get something better than n to the log n size.
Okay.
Can I ask a question? Amir, this is KV. Thanks for the nice talk, lovely talk. So one question, does it, I mean, I just feel that if you want to understand the local neighborhood around 0, wouldn't you need to understand also what polynomials are computed by sigma pi sigma? I mean, it seems to be also giving you about that, right?
Yes. Basically, so I just mentioned it because see, at the beginning when we had this heating set, I was very optimistic because it said, the inverse function theory, things are continuous, and that's it. And then I realized, they are continuous at every point, but not at 0. So I just wanted to mention it so that that's another way to look at it. But of course, right, I mean, constructing robust heating set, that's the main thing. And to construct a robust heating set, you need to understand the structure of polynomials in your set, right? And so, I mean, you can say that I'm just shoving the problem, just pushing it to a different place, but it's the same difficulty. But still, I think that having a heating set for dense non-trivial classes is interesting.
The fact that you already have a heating set is interesting. Is of course good.
Of course, I mean, you can, there's also, I could have mentioned something trivial. For example, consider all polynomials whose constant term is non-zero. Okay, this is clearly a dense set. And you have a trivial heating set for it, just evaluate the polynomial at the 0 point.
Correct.
But what's the difference between this heating set and what I said? The difference is that the class of all polynomials with non-zero constant term is not computational in some sense, right? We don't have an efficient way to compute, a natural way to compute polynomials in this class, right? And so what I expect is, and you already know that, right? If you want to compute a heating set for all degree polynomials in n variable, the heating set must be exponential. And this is again because the set that I described, if you want to compute a generic polynomial, you need exponential size computation. So in our model, the heating set works for a set that has polynomial size computations. So it gives you maybe the intuition that perhaps you can take the heating set and use the fact that the computation for the dense subclass is polynomial, and then make it robust with only a polynomial or quasi-polynomials or sub-exponential blow-up.
Okay.
That's
okay. Thanks.
Any more
Yes,
questions?
you need to understand the class to do something about it. That I agree. And by the way, I also didn't mention, but the quest to make the heating set robust or to prove low bound is, again, it's very related to one Raz's paper on elusive functions. Because, right, I mean, okay, I don't want to get into it, but if you start thinking about the problem, you're naturally led into the question of which polynomials vanish on coefficient vectors of things in your orbit, and then this is kind of similar to evading some varieties.
Okay. Any more questions? Okay, good. Okay. Yeah, let's thank Amir. Thanks, Amir, for the talk.
Thanks, everyone. And sorry for going over time.
Yeah, that's okay.
So thanks. I'll go to the link that you sent me that if people want to talk and ask questions.
Okay, sounds
Okay.
great. Okay.
So thank you very much and enjoy the conference. Bye-bye.
Bye. Thank you.